Okay, this is the second lecture for 16th of March, 2020. And so for this, I am going to work through example problem 938 that is in our notes. We started this problem last Wednesday. I'm going to go ahead and start from the beginning again, work through this problem, and go through how to deal with, which this problem deals with how to look at a air standard Brayton cycle where the isentropic efficiencies of the compressor and turbine are not 100%. Okay, so we started this problem on Wednesday, and I'll go ahead and recreate what the notes for that were. Where if we were looking at this Brayton cycle on a TS axis, we start here at 1, and then if it were, and this is the, of course, compressor inlet, that's the start of the Brayton cycle, and if this were isentropic, we would go up to state 2S, then state 3. So as it goes from 2 to 3, we're going through the combustion chamber. We're adding heat to our working fluid. And this would be state 3. Now, of course, because this is not 100% isentropic efficiency on the compressor, we're going to come this way a little bit. And so our curve going from 2 to 3 is there. This is actually state 2. And that's state 3. And then, of course, as we go through a turbine, if we were isentropic, we would have a vertical line here. So this would be 4S. Of course, we're not isentropic, so we're going to come down here to state 4, which will have a slightly higher enthalpy. And so this is our curve. So this is what our Brayton cycle with non-ideal compressor and turbine looks like on a TS chart. And so in class, I asked you to work out what are these equations for the isentropic efficiency of the compressor, which our problem gives us is 83%. And we worked through that and showed that, as you can find in chapter 6, of course, the isentropic efficiency of a compressor is going to be H2S minus H1 on the numerator and H2 minus H1 in the denominator. The isentropic efficiency for the turbine which we're given is 87%, is in the numerator the actual H3 minus H4, change in enthalpy, divided by, in the denominator, H3 minus H4S. So we're going to use that information in our problem. As with most of the cycles that we've dealt with, the first step that we are going to do is find our state properties. So for this, we have, I'll say the state, T, which will be in Rankine, P, which is in PSI, H, which is in BTUs per pound, PR, and VR. Again, this is an air standard basis, not a cold air standard basis, and so we are well, looks like I didn't quite do that right, but we're going to be using our table A22. So air standard analysis we use table A22, and of course we're in English units now. Okay, so for state 1, we're given that the temperature is 520 and the pressure is 14 psi. So that from our table will show us that H is 124.27. I'm going to do this, give myself a little bit more space. PR is 1.215, and VR, which I don't think we're actually going to need, but is 158.6. Now, in order to find the actual value at state 2, we're going to first have to find out what the value of enthalpy would be at state 2s. We know the compressor ratio is 14, and that is P2 over P1, and it's also equal to P3 over P4. So we're going to be able to work between PR values and P values for our ideal isentropic processes pretty easily. So in that case, at state 2, the P, actual pressure, should be 196 psi, and PR at state 2s will be 17. If we go in and look at our table, we're going to have a value of PR at 17 right between two values, and so for this chance I chose to do some simple averaging and say that that T at state 2s is 1100 Rankine, which would give us an H value at 2s of 266.0. And for that, again, I just took the average of the values at 1080 and 1120. So yes, linear interpolating, but very simple. Kind of gives us a little bit closer than choosing one of the two values. I can now come over here and say, okay, for this compressor then, using our equation above, H2 is H1 plus H2S minus H1 divided by the compressor efficiency, which was, again, 83%. So H2 is then 295.03 BTUs per pound. This is no longer an isentropic process, so we don't have values for PR and VR there. We are just going to work off, if we were asked what the temperature was at that point, it is a little bit off from 1100, but we are working off the assumption that the pressure at both of those is still 196. Remember, when we draw that, this line here is an isobar. Okay, so there, we've got some of our processes. Now, from 2 to 3, of course, that is not an isentropic process, but we were told up here, and I'm sorry I didn't write out all the variables up front, but we were told that the temperature at the turbine inlet is 2500 Rankine, and so that the turbine inlet is, of course, state 3. So we know that temperature, we know the pressure has to be the same, and because we know that temperature, we know that H at state 3 is 645.78 BTUs per pound. PR and VR we can get off the table again. We really only need PR for the Brayton cycle, so 435.7. For an isentropic process going from 3 to 4s, we would have, again, that ratio of 14 between those two states, between 3 and 4s. And so PR for 4s should be 31.12, which is very close to 30.55, which is the value at 1280 Rankine. And so the enthalpy at that point, which would be the enthalpy for 4s, is 311.79. Now we can come back here and use our equation from above, rewrite it so that we say, okay, H4 in terms of H3 and 4s is H3 minus 0.87, that's the efficiency of our turbine, times H3 minus H4S. So this is 0.87. We know these values for H3 and H4S from our table, and so we can find that the enthalpy at state 4 is actually 355.21. The temperature will be a little bit lower, or sorry, a little bit higher than 1280, of course, but we don't need to know what that is. We just need to know the enthalpy. And so now we have the enthalpies for all 4 states. And we can move on to solving for A and B. So A asks us to find the thermal efficiency of the cycle. So the thermal efficiency of a cycle, eta, no subscript there, is, of course, the work of the turbine minus the work from the compressor divided by the heat in. We've already covered previously that for an air standard Brayton cycle, that is H3 minus H4 minus H2 minus H1 divided by H3 minus H2. And we've derived that several times in class. So this, when we put in our values above, and I'll leave that for you to do, is 34% approximately. So for B, we're asked to find the actual net power in horsepower. So the net power is the mass flow rate times the work of the turbine minus the work of the compressor. So that's the mass flow rate times H3 minus H4 minus H2 minus H1. And of course, we found this above. This right here, I'm doing my calculations above, is 119.81 BTUs per pound. So I found that when I was finding the the thermal efficiency of the cycle. So now we just need to know the mass flow rate. Well, for this problem, we were given a volumetric flow rate. And so, of course, to get a mass flow rate, we need the volumetric flow rate times or divided by the specific volume. So the volumetric flow rate divided by V1. So what is the specific volume at V1? Well, to find that, we're going to need to use the ideal gas law. So specific volume at V1 is going to be mRT1 over P1. Start with R in English units is 1545 feet pounds force times a pound mole, or divided by pound mole over times degree R. We ultimately want that to be have units of mass, not moles in the denominator, so we'll divide that by the molar mass of air. Of course, multiply that by the temperature divide it by the pressure, which is 14 pounds force per inch squared. Our volumetric flow rate was in cubic feet, so we want to get all of our volumetric units or length units in feet. So there are 144 square inches and a square foot. So now if we take all this and get rid of, cancel out our units, pounds force cancels out, Rankine cancels out, pound mole, inch squared, and now we have feet cubed in the numerator and pounds mass in the denominator, which is what we wanted. So the specific volume is 1,375 cubic feet per pound mass. So my mass flow rate is my volumetric flow rate. I'm going to put this in pounds mass per hour because that's going to make the conversion to BTUs from BTUs per hour to horsepower a little bit easier. And then divide it by the specific volume. And so the mass flow rate is 43,636 pounds mass per hour, which means the total work is, again, this mass flow rate times 119.81 BTUs per hour. So that ends up being 5.23 times 10 to the 6 BTUs per hour. It's not very clear. Which is approximately 2069 horsepower. Okay, so that is the solution to problem 9.38. And of course, you have a problem on your homework that will ask you to both deal with an air standard cycle, a Brayton cycle, where the isentropic efficiencies of the compressor and turbine are not 100%. The last thing that I wanted to touch on, and really just to kind of put this in perspective, not because we're going to deal with any problems that specifically ask you to understand gas turbines for aircraft propulsion. I just wanted to point out how in these gas turbines, both for aircraft propulsion, but also for portable gas turbines that will be used for power production, everything is in one, combined unit, that this air comes in, the compressor here is, got blades just like a pump would. The combustors heat up, so these compressors compress the air, combustors heat up the air, goes through the turbine where we get the power out, and then the product is gases out. Now, what you'd see for aircraft propulsion, however, is that this, the product, the gases out, that's going to contribute to thrust. And that's an additional concern that we're not going to deal with. Again, I've said before that for aircraft propulsion, for jet turbines, there's a lot of fluids that go into that, and so we're not really going to go into that. But I wanted to point out what these processes are. From A1 to, from A to 1 as it goes through this diffuser, the pressure increases in our diffuser as the air decelerates. So that's what the diffuser does. And there's actually a lot of deceleration and acceleration processes that are going on with the working fluid going through a turbine. And that usually is assumed to be isentropic. From 1 to 2, again, these are kind of the models that we would have. You'd have an isentropic compression. From 2 to 3, you have this constant pressure heat addition, just like we had in the combustion chamber in our earlier Brayton model. From 3 to 4, you have what's usually assumed to be isentropic for an ideal situation again. Expansion through the turbine. Work is developed. And then from 4 to 5, which is the nozzle, the air accelerates and the pressure decreases going there. So for thrust, this is the overall change in velocity of the air. And so that's a completely different situation than we've been dealing with. I just wanted to kind of introduce you to it. And so you'll see here actually this process going from A to 1 to 2 is that isentropic increase in temperature, increase in pressure as well as you go through the compressor. And then from 2 to 3, you have primarily the temperature increasing, certainly the enthalpy of the gas increasing. And then from 3 to 4 to 5, it's the turbine and the nozzle combining together to get a change in velocity of the air. An afterburner would be here you could have an afterburner. And that would give you more thrust, ultimately. Again, we have whole class on jet engines, but just to kind of point out that we have been dealing a lot with the change in enthalpy from the perspective of getting electricity out of our engines, or in the case of, or at least from the Brayton cycle and for the Rankine cycle, getting some kind of mechanical energy out of that. But it is also changing the velocity of the air, and that's the primary goal for aircraft propulsion. Same exact setup, largely, or same philosophy. We're just trying to look at a different change of energy. All of thermodynamics is, again, dynamics, changing, moving energy from one state to another, from one place to another. And so we can change the energy of combustion, heating up the gas, and turn that high movement of high pressure, high temperature gas to a low temperature, low pressure side. We can take that out as kinetic energy that we use for creating electricity, or that we use for creating thrust in an engine. It's still changing energy from one format to another. And that ends our discussion of Chapter 9. On Wednesday, we are going to look at the next chapter, which is refrigeration and heat pump cycles. We're going to start a whole new unit. This right now covers everything we've covered in Chapter 9 is going to be on the next exam. So exam 2 in this class, which we will be doing remotely. And yeah, I'm excited to move on to the next section. You should have everything you need to do homework 6 on Wiley Plus. And you will be asked to respond to some questions on Blackboard that come from this. Thanks.